Hi everyone, welcome to the next video. We're going to be talking about differentials and local linearity. Here are the objectives, and let's get started. So a function is said to be linear over an interval if the difference quotient turns out to be a constant. You remember that the difference quotient is f of x plus delta x minus f of x all over delta x. And so basically it's the slope, right? We're talking about the change in y over the change in x. So when that's a constant, that means that the function is linear. But if you had a curve, which you can see here on this diagram, if you have a curve, this is a quadratic function, and a tangent to that point, if I put this curve, if I graph this curve on a calculator and I just kept zooming in and zooming in and zooming in and zooming in here at the point of tangency, you would begin to see this right here, which is the graph of this function tends to become linear the closer and closer and closer it gets to that point of tangency. So that's what's being called locally linear. So if you zoom in enough times, if it's differentiable, which means if it's continuous and every point exists here, if you zoom in enough, you're going to be able to see that this turns into a straight line. So you can see here that you have the definition of a derivative, the limit definition of the derivative. And you can see that it's the limit as delta x approaches 0 of the difference quotient. So what we have here is, since delta x is very, very small, we can approximate the derivative by using this formula. All right, so what we want to do is we want to just kind of rearrange it a bit and say this, that if we approximate it, f prime of x is close to the difference quotient, the closer that we get into it. So we have f of x plus delta x. Notice that we're just taking off the limit. We're not doing an exact definition, we're doing more of an approximation. We're approximating. Okay, so if we rearrange this a bit, like for instance, we take, we multiply both sides by delta x, right? So delta x, f prime of x, is approximately this. And then we add that f of x to the other side, then we end up with f of x plus delta x, f prime of x, is equal to f of x plus delta x. All right, so the function of x plus a little bit is equal to the function of x plus a little bit, right, because this delta x is a very, very small amount, is equal to the function plus that little bit times the derivative. So here in words is what I said before. It says the value of the function at x plus a little bit equals the value of the function at x plus the product of the derivative of the function at x with the little bit, or multiplied by the little bit. And that's what that looks like. So we're going to use this formula to approximate the value of a function, and or we're going to use it to find the error of an approximation. So here's an even better way, and it's using this idea that the definition of a derivative is definition of a derivative is the slope of the tangent line at a point. And so we know also that we can write the equation for the tangent line by using something like this diagram. So I've got this lovely little curve that I just kind of sketched on here. I don't know if you can see it, but it's this one right here, right? And then here's your tangent at a point. And the point that we are tangent to is the point A, f of A. All right, so remember that to write an equation, you need to have a point and a slope. All right, so my point is the point of tangency, and the slope is going to be the derivative at that point A. Okay, so that would give me the equation of a line. I would say y minus f of A is equal to f prime of A, the slope, times x minus A. All right, and I'll be solving for y. All right, so here's the thing. What we're doing is we know that, say for instance, this is A. I've got A written here, which looks like a 9. But say it was 9, right? Say we had 9 and we had the square root of 9, which was 3. And then this somehow curve would be the square root, which it's not, but it kind of looks like it sort of could be. So anyway, what we want to do is we want to approximate a value that's really close to it, really, really close to the point of tangency without being, so we're taking the point of tangency and adding a little bit, that delta x to either side. All right, so on the next page, we're going to use this. This is a better way because you have the point, A, f of A, and then you have a slope, right, the point and slope at f prime of A, and then from a point and slope, you can write the equation of the line, and we'll solve for y. So let's use everything that we've talked about before to find the approximation of the square root of 9.01. All right, so the first thing we want to do is we want to select or figure out what f of x is. So f of x is going to be equal to the square root of x because we're taking the square root of the number. X that we're going to use in this case is that we're going to let that inside number, that 9.01, the 9 with a little bit added to it, be x. Then for A, we're going to select a number for A that's very close to 9.01. And so in this case, it just seems very obvious to use 9. All right. And then we're going to take the square root of 9, right? We're going to take f of 9, and that would be our point. So this is 9.3 is our point, A, f of A. Now we need the derivative. So the derivative of the square root of x is 1/2 x to the negative 1/2. So if I write it that way, I've got it. But I don't want f prime of x, I want f prime of A, and A is 9. So I'm going to do 1/2 square root of 9. The square root of 9 is 3, 2 times 3, so this is 1/6. So let's write it out. So I've got y minus f of A is 3 equals f prime of A is 1/6. X is 9.01, that 9 plus a little bit, minus the 9 that we're using to approximate it. Okay, and so then when you put this in the calculator, hang on, so I paused it a minute. So y is going to be 3.000, nope, too many zeros, 001666666, it goes on forever. Okay, and if I take the actual square root of 9.01, I'm going to get 3.001666,204. So that's a pretty darn good approximation of that number. So here's one thing I want you to remember, because obviously I can throw in my calculator the square root of 9.01. You know, that's easy. Why do I need calculus to do that? So the idea is that we are looking at this idea of being locally linear, and once again practicing using the point-slope form of a line to find the equation of a tangent line. That's the most important thing that we're learning here. Okay, so here's another one that we could use to approximate 3.98 to the 4th power. All right, so the first thing we want to do is we want to determine our function and our function is x to the fourth power. Our x in this case is going to be 3.98, which is really close to 4, right? Very close to 4, just a little less. So I'm going to use 4 as my approximating, which would make f of 4, f of a, would be 4 to the fourth power, which is 256, because it's 16 times 16. I have a hard time writing. Okay, so then I take the derivative, right, at a would be 4a to the third power. F prime, a is, what is a? 4, is going to be 4 times 4 to the third, which would be 4 to the fourth, which is also 256. All right, so we'll write out we have point and slope, and so I have y minus 256 equals 256 times x minus a, all right? So when you put that in your calculator, do this part first, then multiply, and then add, you end up with y equals approximately 250.88. If I put 3.98 to the fourth power in my calculator, I get 250.9182722, and you're going to get some slightly different depending on what you pick for your A. But that's a pretty good approximation. So, so far we've talked about the different notation that we use in calculus. Y prime, f prime, dy dx all mean the first derivative. Now, differentials, we're going to take this as this dy dx as two different real numbers. So the change, you know, the derivative with respect to y over the derivative with respect to x. So as they become, dy dx becomes a real number ratio. And also, if f is differentiable at x, then this dy dx is equal to the derivative. So we would have this ratio is equal to the derivative, and you would have something like this. So dy is equal to the derivative of x times dx. So you may be asking yourself, why on earth are we doing that? Well, because this is an alternate formula. Remember that the change in y is really equal to this from the difference quotient. dy is the change in y, and dx is equal to delta x. So this is approximate. This is an approximate value. All right, so dy is going to be a dependent variable, and it depends on the values of x and dx. So be sure you have this written down as an alternate formula to the one that we did before. Okay, so let's use this alternate formula to estimate the change in area when the radius of a circle is increased from 3 to 3.04. Okay, so we have the area of a circle, which everyone remembers, pi r squared. If you take the derivative of that, that's 2 pi r. Okay, so we would have that the derivative, dA, remember we have dA dr, the derivative with respect to r, is going to be approximately equal to the derivative of a. So if we rearrange, we end up with the derivative of a equals a prime dr. Okay, so the dr is the change, so that's going to be 0.04. R is going to be 3, right? And so we have dA equals 2 pi r dr. So if we put in the values for that, we have r is 3 and dr is 0.04, and this is 0.754. So if you change the 9 pi if you compare the 9 pi to the 3.04 squared pi, it's a pretty good approximation. It's pretty good, it's close, okay? One more. So we have the radius of a sphere is measured to be 4 centimeters with a error of plus or minus 0.01 centimeters. Use differentials to approximate the error in the surface area. Okay, so the surface area, the surface area of a sphere is 4 pi r squared. So ds, we'll just call it s, dr is going to be 8 pi r. So ds is going to equal 8 pi r dr, right? R is 4. Dr is plus or minus 0.01, right? So if we put that in there, pi, r is 4, and this is plus or minus 0.01, and that's going to equal plus or minus 1.0053, and that would be the error. So you can see here that it's talking about the accuracy of the linearization. And so it should kind of make sense that the closer you are to the point of tangency, the less error you're going to have. The further away that you're moving from the point of tangency, you can see that it gets further and further away, and that's going to be where the error is. So here's an underestimate, here's an overestimate to it. Because here's the point that you're finding, right? You're finding something along the derivative, you're using the derivative. And so that error is going to get more and more pronounced as the further you get away, the further that you get away from it. So I hope you took good notes. I have a feeling you're going to have some questions, and so be ready with those when we come to class next time. So take care, and we'll see you then.